Good morning students. Today we are going to start a very important and very scoring chapter of physical chemistry, that is chemical kinetics. As the name suggests, it deals with speed of chemical reaction. Now think about daily life. When we burn a piece of paper, it burns instantly. But when an iron nail is kept in air, rusting takes place months or even years. Why it is so, ma'am? Both are a chemical reaction, but their speeds are completely different. Why do some reactions happen very fast while others are very slow? Can we control the speed of reaction? How do we measure the speed of reaction? All these questions are answered in chemical kinetics. So let us begin with the very basic concept, that is rate of reaction. Rate of reaction simply means how fast reactants are converted into products. How fast reactants are converted into products. In chemistry, we measure this using concentration. So, mathematically, it is defined as change in concentration. Rate is defined as change in concentration per unit time. What I said? Rate is defined as change in concentration per unit time. During a reaction, reactant is converted into product. So, with time, reactant concentration is decreasing and product concentration will be increasing. So, this can be expressed in two ways. Rate is equals to negative of minus delta R by delta T. Here negative sign denotes that reactant concentration is decreasing, right? And for product, what we can write is rate is equals to positive of change in concentration of product per unit time. Here positive sign denotes that concentration must be increasing. Okay, negative sign denotes that reactant concentration is increasing with time, while positive sign denotes that product concentration is increasing with time. This sign conversion is very important for problem solving. Now that we know how to measure this rate, the next question is, on what factors does this rate depend? Why do increasing temperature makes the reaction faster while powdered solids reacts faster than larger pieces? So let us discuss the factors affecting the rate of reaction. Factors affecting rate of reaction. There are several factors affecting rate of reaction, but we'll focus on the most important one. First is concentration. If concentration is increasing, what that means? It means that more particles are present per unit volume. More particles are present per unit volume. This means that they will ultimately lead to more collision, and that will ultimately leads to faster reaction. So it means reaction concentration, if reaction concentration is increasing, then rate will also increase. If concentration is increasing, then rate will also increasing. Okay, so next factor is temperature. If temperature is increasing, what that means is, if temperature is increasing, more particles will give more kinetic energy, and that will move faster, and that will ultimately lead to more effective collision. So, if temperature increase, that will make the reaction faster. That means rate will increase. Okay. And the last factor is catalyst. As we all have studied since childhood, that catalyst increases the rate of reaction without being consumed. Without being consumed, it increases the rate of reaction. So catalyst increases the rate of reaction without being consumed. It provides an alternative pathway basically with lower activation energy. So it's provide an alternative pathway with lower activation energy. Activation energy is denoted by EA. Low activation energy, rate of reaction will increase. Okay. So these, among all these factors, concentration plays a central role in rate law. Now let us discuss how concentration depend on rate mathematically. This brings us the idea of rate law. So what we are going to study is rate law. How concentration affects rate mathematically. So rate law is basically defined as, it is an experimentally determined relationship between rate of reaction and concentration of reactant. Okay. So for a simple reaction, a reactant is converted into product. Reactant is converted into product. So rate is proportional to, or we can write this in a much better way. A is, suppose reactant is our A, is converted into product. So what we can say is rate is proportional to concentration of reactant raised to some power. So how can we express this? Rate is equals to K A N. Here K is the rate constant, A is the concentration of reactant, and N is the order of reaction. So K is rate constant, A is concentration of reactant, and N is order of reaction. Order of reaction basically tells us how strongly concentration affects rate. Now depending on the value of this exponent n, that is order of reaction. Reaction are classified in various orders like zero order, first order. In our syllabus we will discuss the most important ones, that is zero order reaction and first order reaction. First we will discuss about zero order reaction. For zero order reaction, as the name suggests, its order must be 0, that is n is equals to 0. For zero order reaction, rate doesn't depend on concentration at all. Even if concentration changes, rate remains same. So for this we can write as rate is equals to this, because n has value of 0. If we write the earlier formula, that is n value is 0. So 0. What this means is rate is equals to K. That's why we say rate doesn't depend on concentration at all and zero order reaction. Right? Right. Now, why this happens? This situation usually occurs when reacting surface is saturated, such as reaction on catalytic surface. Okay. Now that we need to know how concentration affects time. We need to know how concentration affects time. For that we use integrated form of zero order reaction. So for integrated form for zero order reaction, is A is equals to A naught minus KT. This equation, what this equation clearly suggests? This equation clearly suggests that with time concentration is decreasing linearly. With time concentration is decreasing linearly. Now let us understand about half-life in zero order reaction. Half-life, what this name suggests, half-life basically means is time required for consumption of A to its half value, or basically we can say time required for concentration of A to become half of its initial value. If suppose initial concentration is A naught, then after half-life, after one half-life, half-life is noted by T half. If initial concentration is A naught, then after one half-life it will be A naught by 2. Okay? Okay. So, the expression for half-life is A naught by 2k. Observe carefully now. From this equation is for zero order reaction. From this equation we can say that half-life depends on initial concentration. So, if we take large amount of reactant, then its half-life will be larger. Okay, its half-life will be larger. So, half-life depend on concentration directly. If initial concentration doubles, then rate also doubles. Okay. Now moving towards the most important case, that is first order reaction. For first order reaction, rate depends on concentration. Rate depends on concentration. If concentration is increasing, rate also doubles. It can be expressed in this way. A is converted into product. Then according to rate law, what we have expressed earlier is rate is equals to k raised to power A power some n. Here we are talking about first order reaction. That means n value is 1. So, n value is 1. So, rate will be R is equals to K into में A. So, from that we can see rate depends on initial concentration. If initial concentration increases, then rate also increases, right? Right. Now, if we talk about the integrated form for first order reaction, then integrated form for first order reaction is basically ln A is equals to ln A naught minus KT, or we can write this equation also as K is equals to 2.303 by T log of A naught by A. Okay, this formula is very important for problem solving, so remember this. Now if you talk about half-life in first order reaction, then half-life for first order reaction is basically 0.693 by K. Now observe clearly, half-life doesn't depend on initial concentration. There is no term in this formula such as initial concentration, right? That means half-life doesn't depend on concentration at all. No matter what we take, how much we take reactant, half-life remains the same. Half-life remains the same. This is a very special property for first order reaction. Radioactive decay follows first order kinetics because of this reason. Now suppose if half-life is 10 minutes, then after 10 minutes the amount that will be remain as 50% left. After 20 minutes, left will be in case of after 10 minutes. After 20 minutes, what amount of percentage will be left? What amount? 25%. And after 30 minutes, how much amount would be left? %12.5%, right? So this is very important case. We have to remember this. These are the conceptual questions that are that's asked in the exams, right? Now that we know both about zero order reaction and first order reaction, let's compare their half-lives. So for zero order reaction, and first order reaction, for zero order reaction, what the formula was? T half is equals to A naught by 2K, while for first order reaction, T half is equals to 0.693 by K. Now as we can clearly see, in zero order reaction, half-life depend on initial concentration, while in first order reaction, half-life doesn't depend on initial concentration at all. So if examiner asks which reaction has constant half-life, it will be first order reaction. And if the exam asks which reaction depends on initial concentration, which reaction? Zero order reaction. So these are very conceptual questions that are asked in the exam, so we must know about all these things. So what we have today understood is, what we have today discussed is how rate is defined, what factors affecting it, how rate depend on concentration, and also what we have studied, how reactions are classified in different orders. And most importantly, we have discussed how their half-life behavior depend on concentration, which is very, very important for exam point of view. So if these concepts are clear, then chemical kinetics become one of the most scoring subjects of physical chemistry. In the next class, we'll discuss about more problems and we'll apply the concept in that problems. Thank you very much.